Okay. Ladies and gentlemen, I now want to address the low bias, high variance issue. And the answer is random forest. So what is random forest? It was proposed by an eminent statistician, Leo Breiman, in 2001. He was a really interesting guy, by the way. He didn't write many papers in his life, but the ones that he did write, were very profound and original. He was an out-of-the-box thinker. And he proposed this method, which actually had been proposed a few years earlier by Amit and Gini, only nobody noticed at the time. And now random forest has, bias practically as low as decision trees, but much lower variance. And what it is an ensemble of decision trees. So it's a collection of decision trees that make an average decision. Now, if we put all of the training data into a deterministic routine for constructing decision trees, then if I do this t times, then I will get t identical decision trees, and I have not gained much. Yeah? So obviously, I must make some changes from constructing one decision tree to the next. And what Breiman proposed was to inject two sources of randomness. And it turns out that both sources of randomness are really important. So both make a difference. The first one is to sample with replacement from the original training data. So each tree sees different training data. And this new training data is sampled with replacement from the original training data. So the stochastic model of this is an urn. Now we have an urn, that's a box in which you're in this box are all our training exemplars, and then you are supposed to pull out a training exemplar, pull out without looking, and then to put it back inside the urn. And then you shake it and you pull out another one, and you put it back, and you shake and repeat. And so what this means is that if you have n original samples and you all put them in the urn and you sample with a replacement, then usually there will be certain samples that you pull out several times, and there will be others that you don't pull out at all if you do this process once. And then you do this repeatedly, and you train one decision tree for each one of them. And so each tree sees different training data, which is sampled with replacement from the original training data. This process here is called this is a bootstrap sample. And I think the name, I'm not totally sure, but I think the name comes from this story of Münchhausen. So this is in German culture, this is a story about somebody who got stuck in the swamp, and then the guy pulls himself out of the swamp on his own bootstraps, which of course is not physically possible, but it makes for a nice story. And statisticians like this also. So that's a bootstrap sample. And actually, Breiman called this process here bagging. Which comes from bootstrap aggregation. You see there's a B in here and there's an ag in here, and this is why he calls it bagging. All right, so if we do this capital T times, then we get T pseudo different trading sets, and we get capital T different decision trees out. That's one source of randomness. The other source of randomness is, so far in the greedy tree construction procedure that we discussed so far, we've always used the best split. So it's greedy also in that sense. So it was greedy in two senses. Greedy that we always take, the nearest best decision, but we always insist on picking the decision which locally looks best. Well, and if we construct a single decision tree, that's what I would advise. So to construct a single decision tree, yes, you would really iteratively choose the very best split that you can find. But if you have an ensemble, it actually turns out to be better to inject a bit of randomness in there also. Namely as follows. In each tree that you will build, and at each node, you consider only a random subset of features in your quest for the optimal split. So let's say we have 17 features. In standard decision trees, you always, at each node, you try out all splits along all 17 feature dimensions. In this method, you pick a random subset. Let's say you randomly pick 3 out of your 17 features. And then for these 3 features, you again try out all possible split positions. Doesn't sound like much, but it makes a huge difference in performance. This is called a random split selection. And together, this is random forest. Now, this random forest, it has it comes with 2 nice features or gifts for you. Two bonus, I don't know what to call them, bonus features. One is the so-called out-of-bag error. You remember we had the bagging further up, and so each tree saw one of these pseudo trading sets, and then for that particular tree there are a couple of trading examples that it had never seen during its train time. And then we can use those extra samples to let that tree make a prediction on them and see how well we do. So we make a prediction. For samples not used in the construction of that tree. This is, of course, very reminiscent of cross-validation that we discussed last time. And overall, this is an inbuilt estimate of generalization performance. So confer cross-validation, yeah, very similar idea. And secondly, we get what Breiman called the Gini importance. Breiman used as impurity criterion this Gini measure. And in Gini importance, well, we use only a random subset of features, but for those features, we still look for the best split. And then we do this for all the nodes in a tree. We do this for all our capital T trees. And then we can just make statistics and count how often was a particular feature used for splitting. And the more often it was used, the more important we conclude it is. So we count for each feature how often it was used for splitting. And this is what one of the, there's this public OneNote file where you find these figures here. This is where they are from. This is work by Björn Menze when he was still a PhD student in Heidelberg, and a few colleagues from Merck company. And actually you might know this guy. He is in physics and studying biophotonics. Peter Bachert is a guy at Cancer Research Center. And we looked at the classification of spectra. And this is something that many people have been interested in for a long time, yeah? In a field called chemometrics. And at that time, we looked at random forest versus all these tools that these people had been developing over years. And I mentioned earlier today that we had a few data sets. One of them was a magnetic resonance spectrum. And then we had two populations, and there were serious data sets, like classifying different sorts of bacteria. And there were not so serious data sets, classifying this wine versus that wine. But in any case, we have spectra. And in the example that I show here, these spectra have 1,500 channels. So that means we have 1,500 features. And this is an example of features which are highly correlated, of course. Because if you look at the spectrum, it usually doesn't look like white noise, but we have more or less white peaks. So the measurements at two adjacent bins or channels for sure are correlated, but also due to the nature of whatever you are studying, it can also happen, if we take spectra from the atmosphere or so, and we know that yes, in the atmosphere we have water, and water contributes in several regions to the spectrum, then of course we have, let's say, correlation between here and here and there. So whenever we measure a lot here, then we're going to measure a lot there and a lot there, because there's water in the atmosphere, for example. So we have these correlations, local but also non-local ones across the spectrum. Good. And now when we have two groups, like two strains of bacteria which we want to classify, then we can ask, for example, for each channel separately, how well separated are the groups by this, are the two groups by this channel? So we can look at channel whatever 450, and we can ask what's the average absorption of the one group and what's the average absorption of the other group. And if they are very distinct, then it's probably a useful channel, and if not, then it's not a useful channel. And when we ask this question, distinct or not, we can, there are many ways to do this, but one way is to do a statistical hypothesis test, and then here p-value would tell you, how distinct do they look, or how improbable is it that they are truly from the same class. And then we can all take these 1,500 p-values and we can just sort them. Yeah? So if we sort them, we get 1,500 rank orders, and what you see here is which spectral regions are important. So spectral regions that are important are this one, and this one, and that one, and that one, and that one, and so on. So this would be a conventional chemometrical way, let's say, but you can also instead use this Gini importance that we've just been discussing. And if we just compute this Gini importance, then we find this curve on top. So what we see here is this Gini importance. And now we can again sort it, and we again get these 1,500 values. And now if you hold them side by side, you see that they often agree. So both think that these spectral regions are important, both agree here, but there are also regions where they disagree. And if you now plot one against the other, then you can get a plot like this. So where a univariate importance measure thinks that this channel is informative, then this Gini importance will also think so. So we have a correlation here. But but we have these cases where certain channels, they don't seem useful from the univariate standpoint, but random forest still somehow knows how to profit from them by using these features not alone, because alone they're not informative, but by using them in conjunction with others. By making a split first along this dimension, then along that dimension, and so on. So this is from a lot of real-world data where you see that this very, very simple recipe here, Gini importance, can actually give you, some things that classical methods cannot. Now it has its limitations. This Gini importance, for example, it is biased towards features that have many categorical levels over features that have few levels. But it's super simple, it's super cheap to compute, and it's sometimes really useful. Good. So, what's my random forest summary? You see, this is a lot of advertisement here that I'm making for random forest, but I've not invented it. I'm not getting any money for doing this. It's just a really good method. So it has high prediction accuracy. Without parameter tuning. Now you might object. Actually there were two hyperparameters. One hyperparameter was, let's remember them, hyperparameters. Was on the one hand the number of trees that we are going to construct. So how many bootstrap samples are we going to generate, and how many trees are we going to train? And the other one is this size of the random subset of features. Now for number of trees, the default usually is to take 256. Why? Because 2 or 3 is too little, 10,000 is too much, in the sense that if you look at the accuracy over number of trees, it saturates, and 256 means you can represent in 1 byte what was the decision of that ensemble. So usually you would take 256, or if you are pressed for resources, then perhaps you would only use 50, and if you are super rich, then maybe you would use a few more. But really, 256 is a good number. And then there's the question of size of random subset, and then there are different recipes depending on whether the features are categorical or whether the features are real numbers. There are different rules of thumbs. These rules of thumb are something like the logarithm of the number of features, and it turns out that which rule of thumb you use usually does not have a great impact on the accuracy. Yeah, and this is why I say without parameter tuning, because whenever I can afford it, I use 256 trees, and I use whatever logarithm of number of features, and it will work fine. And you had a question, I think.
How do I actually use that random forest to make predictions? Because I will have a lot of trees,
yeah,
and they might say different.
Yeah, thanks for the question. So how do we actually make predictions? And I, didn't say it explicitly. We, if I do 256 trees, 200 vote for this class and 56 vote for that class, and then I follow the majority. Yeah? So it's like k nearest neighbors. And I'm grateful for the question, by the way, because random forest is not well calibrated, and I should add that to the list of properties. Let me put it above the bonus features. So random forest is not calibrated. That means, this ratio of how many trees voted for orange versus for purple, this will of course depend on where in the feature space my query was located. So if my query was located, did I have a picture somewhere? Okay, excuse me, I will jump to where we were before the break. I was told not to scroll. Okay, all right. So, in those regions, 256 trees out of 256 will agree that it should be purple. In this region, 256 out of 256 will agree that it should be orange. And in between, in this region, we might still get a large majority for one of the classes, but we don't trust, or we don't try and extract meaning from the exact ratio. So what matters is the majority in favor of this or in favor of that, but I don't interpret this truly as probabilities, the numbers that I find. I don't interpret this as the posterior probability for one class or the other.
Why not? Because this actually seems like a good idea, because it can tell me that the purple region on the right is much more defined than any purple region.
Yeah, because empirically, random forest is overconfident. Yeah, so if let me. So on Wednesday, we will start looking at what is this thing, posterior probability of a class. It's a well-defined quantity. And if I compare this on toy data where I know what it should be, if I compare this to what I get out from random forest, then random forest will be too confident. So let's say in a one-dimensional example, the true probability of the one class is a sigmoid like this, then random forest will give me something much, not a step function, but something too steep. And what I mean will become clearer when we've discussed what are these posterior probabilities. All right. Yes?
So why is it important to draw the samples with replacement versus without?
Okay. So I mean, if I did draw them without replacement, then I would have this parameter of how many samples do I want to draw. Let's say I could say I use 70% of the samples each time, but I would have this extra parameter, 70, and each of the trees would have seen a little less, fewer observations. It would only have seen 70% instead of 100%. But I will ask Manuel for a more profound answer, if he has one. You can also say no.
So, in general, the answer in that case is statistics. But for my theory, I think what they like is the bootstrap. It's mostly used to just to pretend that you get more out of the sample. That's where the bootstrap comes from, because you get more information of the distribution. And then if you sample with replacement, then you always sample from the same distribution. If you sample without replacement, then each sample is from a different empirical distribution, so, which may work empirically, but makes the math ugly and also destroys your original hypothesis of I have this empirical distribution, which is hopefully close to my truth, and I always sample from the original. But yeah, looking at your favorite statistics, the bootstrap has been a while.
Okay, so I think actually it would work fine if you used 70%, but I would expect it to work a little bit better with replacement, and I cannot give you a good answer except that the size of the training set is right. I think this is what Manuel was saying. Okay, we take it as homework to give a good reference, okay? Or maybe you find it before the lecture finishes. Thanks for the question. Yeah?
Do the results change if you do a density estimation first and then sample from the density estimation? I mean, the bias should increase because you have to choose the kernel, but...
Yeah, so density estimation in high dimensions, you don't want to do it. Yeah? What you are saying, we could also manipulate the training data by jittering a little bit. Yeah? So I could say, for example, I use 100% of my training data for each tree, but I jitter the coordinates a little bit. And the problem with this is, which is equivalent to choosing the kernel in kernel density estimation, is to say, all right, in which dimension should I jitter how much? Because it could be that one of your features you measured with great accuracy, but the other one with quite a bit of error. But then you would have to tell how much do you want to jitter along what dimension. In general, you may make your data worse than it really is. So that's not really something that's advocated in real life. All right. So we get high prediction accuracy, without parameter tuning. It handles both categorical and continuous features. So if you have on the one hand features of the sort yes, wing or no wing, and on the other hand features that are measured in meters, it can use both at the same time, no problem. And it is still very fast. It is, for capital T trees, it's capital T times slower than a single decision tree, but a single decision tree is really a blazingly fast thing. So it's fast both at train and at prediction time, and it has this inbuilt accuracy measure, it has this inbuilt feature importance, really a nice method. So overall, I would still say, in the age of neural networks, I would still say it's the best off-the-shelf classifier when training data is limited. So if you have a lot of training data, you want to train a neural network. And then it takes quite a bit of expertise to figure out, okay, how many layers and this and that. But if you don't have excessive training data, if you want something that's going to work pretty well right out of the box, then this is it. Yeah? And then if you now start tweaking things, if instead you use a support vector machine and you start, try and optimize the kernel, etc., you might get out an extra % of performance, but not 10% of accuracy. Yeah? So it's really a very, very nice method. Good. Now, to relax a little bit, I'm going to show you an application of this from computer vision. So I'm using here a program that we've created over a long time. It's called Ilastik, and it does many things, but it started with pixel classification. I create a project, I load some data, I always like playing with medical data just because or with biological data because it's pretty. Now this data, I think it's something Gini or something. I don't know it. Also, in reality, it is colorful, but for didactic reasons here, I'm choosing a gray version, and I've not tried the didactics of this before, so I hope it will work. And I am now going to select a few features and then train a random forest on this. So the features here, they have names like color and edge and texture, and then we have features at different scales, and I'm just here going to use a lot of features. And so these features are now being computed for each and every pixel. Okay, maybe it's best if I show you some of them. So for example, this is a smoothing at a small scale or smoothing at a large scale. This is an edge detector at a medium scale or at a large scale. Or here we have some nonlinear features at various scales. And now in your head, imagine that all of these features are being stacked together. Yeah? So my original input was just a single image like this. And now I've computed, 20 or what features. And imagine in your head that these are all stacked. Now each pixel becomes an observation. And then I have these, let's say, p equals 20 features. The spatial context of which pixel is a neighbor of which other was used in the computation, but let's forget about it now. Yeah? So conceptually, we're now switching to a data matrix which has p times n rows and columns. P is the number of features, and n is the number of pixels in this image, 1 million or whatever. Now, so far, they are all unlabeled. And let's say I'm now interested in classifying various structures in there. I'm going to create a total of 3 classes, and I'm going to say, I want this thing, whatever it is, to be red, and I want, I want this stuff to be blue. Have you seen? I've drawn a little bit, and I want that to be yellow. And now when I press on Live Update, it uses these elements that we have just generated by these scribbles and trains a random forest on this. So we could now count, how many annotations did I actually generate? These are maybe, perhaps 30 pixels or something for the red class. Then I had a little bit of, let's say here, I had maybe 30 pixels here for the blue class, and somewhere I had 40 pixels for the yellow class. So my data matrix X was now P, we said was 20 features, and I now had of the order of whatever, 120 or something annotated pixels altogether. And this data matrix was used to train a random forest, the method that we've just been discussing. And now this random forest was used to make a prediction for all the other pixels. And the result here is this, and it's actually not half bad. Yeah? It's also not great, because, for example, I think this thing here on the right-hand side, I would prefer this to also be red, but this is apparently, too different looking from the training data. So if I want to insist, okay, I could, label this a little bit, and now the random forest is retrained, and maybe you've seen that the prediction has actually been updated. Okay, then I could make, this is now sort of an overlay of colors. I could make a hard decision for each pixel and say, if you have to make a choice, what does the majority of trees vote for? And this is the answer. Okay, and with the number of labels that I've given here, it would be very difficult to train a neural network, and especially on a machine like this, it would be very difficult to train a neural network in in real time, etc. So for this kind of application where you have little training data, it's actually a very good method. Now, I mentioned those features. Let's look again at those features. I will now just use pretty much the original color. These are now my features, and let's use the very same labels. So if I zoom in, you see the labels are still there. The red labels are still there, and the yellow labels are still up there, and the blue ones, if I look for them, the blue labels are still there. Okay. Now let's use the very same labels as before. And this is the prediction that I'm getting. And it's still doing something, but you see the prediction has become a lot noisier. Yes. And why is that? Well, because the features that I gave before somehow were more informative than the features that I've used now. And this is what I want to indicate with this sketch here. All of this machine learning always assumes that the features are informative. So here, this is toy data. And again, the pictures are in the public OneNote folder. Here I have the black class and the red class, and I have two features. And yeah, it's difficult to train a classifier to make any predictions here. You pretty much have to be an oracle, somebody who's more than a scientist to get something out of here. But now look, it's the very same features in X1 and X2. But now I've added a third feature. So X1 and X2 are the identical values as before, but now I've added a third feature which was informative. And now we see, okay, the black tend to be up here and the red one tend to be down there. And we can see that it's probably a bit possible to train a classifier. This is the thing about this choice of features. When I was up here, I could use just the gray value at each pixel, and apparently that already does tell me something, because apparently the gray here is a little bit different from the gray in those dots. I mean, it has managed to do something here, but there's confusion here between the blue and the red. It cannot really sort them out. So actually, to a large extent, it's our eye fixing this now. But if I again use the more informative features, and I go back and use the very same annotations, and I train a random forest, and I display the results, I get something, well, which I would call better looking. Okay. So today we have studied a method that works pretty good in real life, but is not very well understood theoretically. And on Wednesday we'll do the opposite. We'll turn to studying the foundation of all of this machine learning. We will talk about what is the very best classifier possible at all, and what is it like. And we will see a method that is theoretically nice, but does not perform as well in practice. That will be on Wednesday. See you then, and don't forget, no lecture Monday next week. Thank you very much.